welcome to another video for physical science. In this video we're going to be discussing motion. So this is the main idea in motion that we're going to be discussing today. A coordinate system is helpful when you are describing motion. So we're going to describe motion using a coordinate system. And these are some of the main questions that we're going to address. What is a coordinate system? How does the chosen coordinate system affect the sign of objects in position? How are time intervals measured? What is displacement, and how are motion diagrams helpful in answering questions about an object's position or displacement? So at this point you might want to pause it and have these main questions written down so you'll know what we're discussing as we move along. Now right quick, as I'm looking at the questions, the second question there, how does the chosen coordinate system affect the sign of object's position? We're actually not going to discuss that in this video. I'll have to save that for another one. So let's go ahead and jump in, looking at the vocabulary words that we're going to be discussing. So it looks like we have, 10 words? Is that right? 10 words. So we have 10 words that we're going to discuss today. So let's go ahead and jump right in. The first 4 words that we're going to look at in terms of position and distance is 0 point, coordinate system, origin, and straight line. So these are the first words that we're going to address. All right, so what I have here is I have a scenario where a random tire is going to be rolling down the street. Okay, this happens, you see this quite often in your neighborhood, right? So again, this is just a random scenario that I'm going to use to help to describe position and distance and how you use a coordinate system to describe motion of an object. Okay, and again, this could be anything that you see going down the street, a person on the bike, a squirrel, dog, what have you. So let's just use a tire for our purposes. All right, so the first term is coordinate system. So as I'm making the coordinate system, if you recall back in the previous video where we had speed graph and acceleration graph, when we were making a graph, one of the important things was labeling the graph right. And in this one, for example, we're labeling it as meters to signify what each of these intervals mean here. All these numbers that you see on my coordinate system, and that coordinate system, you see the straight black line, that's essentially the x-axis on the coordinate system, and each of those lines representing 5 meters. So I have it labeled so that you know exactly what all of this means. You don't want to make a coordinate system graph and not have it labeled and not know what your units are or your time increments are. So the better organized, the more labeled you are, the better information you're going to get from your coordinate system graph. So again, going back to that line that I was mentioning, so this is the straight line, my x-axis that I'm highlighting here. And for the second, I'm going to wipe away all the other things that are basically just serving to distract us right now. And we just want to focus on that line. And that x-coordinate, that x-axis, and then the lines that we have written on that to signify our different increments that we've broken this line up into. Okay, so again, our straight line shows us the direction that our object is going in, and it's also used to make the different intervals that we're going to use, and this is what we're calling our coordinate system. The only thing I have missing here are the actual numbers and the label from meters. Okay, so here we go, let's get back into it. So again, showing which direction the object is going in. We're going towards the right, and this is our object. This is what our point of reference is. This is where we're going to start. Okay, so now we pretty much have our coordinate system complete. And again, keep in mind that this is all used. We're using all of these components to describe motion. Okay, so 2 more terms to discuss is 0 point and origin. So the point at which all variables in the coordinate system have the value of 0. Okay, so just think about that for a second. So this is our starting point. This is our point of origin, or our 0 point. At this point in our scenario, our object has not moved. It's not moving. It's barely just about to start. That means our time hasn't begun. So t will equal 0. Okay. So all values will be 0, so our t will equal 0, and our position, our distance, will also be 0. Now the second that this object moves, our time will then start, and our position will change, if in fact it does need to change, if it is in motion. So now our object is motion. So we have a wheel, somebody pushed the wheel, and now it's just rolling down the street. You know, it occurs to me why I maybe picked this scenario, because as a kid, I remember a couple of times, and this was back in the mid 90s, where you would literally see somebody rolling a wheel down the street. Um, you don't really see that nowadays. But in any case, I digress. So as you can see, our wheel is rolling down the street, and following behind it are dots. Now, in real life, you don't have any dots, but for our coordinate system, I'm drawing dots to signify where my object is moving and where I'm pretty much marking. I'm marking the places that I'm going to use to make measurements. Now, in this case, we're going to assume that our wheel is going at a constant motion. So that means every time that I take a measurement, it's going to be at the same distance, the same difference of distance from the previous point. So our dots are going to be evenly spaced out because of that. Now, we mentioned in lecture today that if our wheel was accelerating, then our dots would be more spaced out. And if our wheel was decelerating, our dots would be more constricted together. They'd be closer together. Which, by the way, I want to take a minute to just give a shout out to my 7th and 8th grade science class at Scenic Hills Christian Academy. Go Hawks! All right, moving on, guys. So, in physics, if an object has a size or a magnitude and direction, then it is called a vector. Okay, so if you recall in our lecture today, we talked about magnitude and direction. So the magnitude is basically the size of the force or the size of the amount that the object moved, be it meters per second or miles per hour. That would be a magnitude. How much distance per time did this object move? So you're looking at your meters, and then you're also going to be looking at your time to find magnitude. But not only does it have magnitude, but it also has a direction. So whenever I'm discussing the movement of an object, I'm describing the movement of an object, I'm going to describe how fast it's going and what direction it's moving in. That's called a vector. Now, of course, not in every scenario, you're not going to always give a direction, right? But for our sake right now, let's talk about vectors and talk about the cases where you do use direction. So our magnitude would be something like the object moved 30 meters and it went west. So when you add the direction component to it, now it's become a vector. And vectors are always used in physics as arrows. They're drawn as arrows. So you'll have a starting point on the left, and then you'll have the end point where the arrow is at on the right-hand side. And that is a vector when you have direction and magnitude. Now, let's say you don't have direction. Let's just say the object moved 30 meters, and there is no direction in that. That's considered a scalar quantity. So if I'm talking about a car moving and I describe its motion as saying it's going 30 miles per hour, that is a scalar quantity. Okay, I'm saying the magnitude of its speed, of its change of position over time, but I'm giving no direction. When I leave the direction out, there I'm talking about a scalar quantity. Okay, so you only have magnitude but no direction in scalar quantities. So here are the difference between scalar and a vector. Scalar, only magnitude, no direction. A vector, magnitude and direction. Okay, so you might want to take a minute to just kind of marinate on that. All right, so far we've discussed 6 terms. We have 3 more to go, so let's dive in. So again, consider that we are talking about the description of an object in motion, and we can get very, very detailed as far as what we're looking for. You know, maybe we're looking for something very specific. Maybe we want to know how fast the object was going from the interval of 5 seconds to 25 seconds. So when you're doing that, you're basically going to ignore everything except what's in that interval. Okay, and these intervals can be different. Your point of reference can change in any which way you want. Depending on what you're looking for, your point of reference is relative. Okay, so in this case, for example, my point of reference would be I'm looking at how fast the object went from 1 second to 5 seconds. So that would be the interval in distance of 5 meters to 25 meters. And then I would have to find my velocity in that case. So recall the formula for velocity is delta d over delta s, or delta t, sorry. So my distance final will be 25 minus 5 is 20 over time final minus time initial, which is 5 minus 1. So that would be 20 over 4. So that's basically 5 meters per second. So in the interval of 5 meters to 25 meters, my object was going 5 meters per second. Now let's say I wanted to find the interval from 2 seconds to 5 seconds. It's the same thing. You're still using your velocity, your distance over time, your delta d over delta t formula to find whatever velocity you're looking at that particular point. One thing that I would say is go back to our speed and time graph, or our acceleration graph, or a speed and time graph actually, and look at how we break down intervals in those graphs. Okay, and let's say you want to find out what the average speed was throughout the whole trip from 0 meters to 30 meters. So then you would do the math for that the same way as before. Okay, so again, your point of reference can be at any point in this graph that you want to find out. Okay, so it can change. Those intervals can change as you want. All right, so we have 2 more terms to look at. So to discuss displacement and distance, let's say, for example, my dog Jerker here ran away from me and he's running around the neighborhood. And I'm describing his motion by saying that he went 1 block right, 2 blocks up, 1 block right again, 1 block up, and then 1 block right. And there's where I caught him. So there's 2 ways of describing the motion that my dog went. Okay, first of all, one of the first initial ways would be what is the distance that the dog traveled, the actual distance that tracing the actual path that he took. So in order to find the distance traveled by the dog, I would have to add all the different blocks that he traveled. Okay, so that would be 1 plus 2 plus 1 plus 1 plus 1, and that would give me a total of 6 blocks. Okay, so he traveled a total distance of 6 blocks. So by definition, distance is a scalar quantity. Now remember, with scalar, I have a magnitude, 6 blocks, but no direction. Okay, so it's defined as a scalar quantity that refers to how much ground the object has covered during its motion. How much actual ground. Now there's another way to describe this motion, and that's displacement. It's displacement. You are displacing something, or it's being displaced from its point of origin. And that displacement actually creates something called a vector, a resultant vector. Okay? So let me explain that resultant vector in a little bit more detail. And in order to, actually before I get to how we got to that, how we got 4.2 blocks, let's talk about the definition of displacement. So displacement refers to how far out of place an object is. It is the object's overall change in position. So compare that to distance. Distance, we're actually following the path taken by the object, whereas displacement, we are just looking at how far it is from the point of origin, from its original position. And that's very different. So to find a vector, to find a resultant vector, what is a vector and how do we get it? One of the things that we need to consider is Pythagorean Theorem. Okay, so let's take a look at that. So we're taking away everything, taking everything out of our screen here, and we're just looking at our vectors. We have our resultant vector in red, and then the yellow vectors that are describing our distance. So how do we find that vector, 4.2 miles? So like I mentioned before, we want to consider Pythagorean Theorem. And in Pythagorean Theorem, if you remember from math, that's basically working with triangles. And that resultant vector is a hypotenuse. Okay, now some of you, I can already feel cringing and giving a big sigh like, oh boy, here we go with math, geometry here. Well, this is where it's actually necessary, and this is how you apply that math that you're working at. So, make sure you're working hard in math because that stuff never really goes away. So here we are, the resultant vector. Again, consider the fact that we're looking at a triangle. So we're looking at the bottom leg. So let me repeat that again so you can see that again. If you look at the bottom leg that are horizontal, we're looking at all the times that the animal traveled in a horizontal position, and we're adding those up. We're adding those vectors up, and those come out to be 3 blocks. So the bottom leg is 3, and now we're going to look at all the vertical components to our triangle. We're going to put them together and add them up, and that adds up to 3 also. So again, with Pythagorean theorem, you have a squared plus b squared equals c squared. I hope this is all sounding familiar to you guys. If not, then in class and lecture we can address this. Now, consider the fact that we're looking for our resultant vector, our red arrow. So we're looking for c, and you notice that c on the right hand side you have c squared. We want to get rid of that squared by square rooting it, and so that means if we square root the left side, or the right side, we have to square root the left. So the length of our resultant is the square root of a squared plus b squared. And again, we found out that the horizontal component is 3 and the vertical is 3. So we replace that. And recall that that's going to be 3 squared plus 3 squared. So that's both going to be 9. So that's 9 plus 9, 18. So the square root of 18 is approximately 4.2. And that's how we got 4.2. So again, in summary, what we're talking about when we talk about displacement is we're talking about the distance the dog is from the point of origin. So another way to look at this for displacement is, I don't know if you've heard the old saying that says, as the crow flies. Well, displacement is as the crow flies. How far is the dog as the crow flies? So for example, a crow is not going to follow the path of the dog and turn right and turn left and right and follow the street. The crow is going to fly the shortest distance from point A to point B. It's going to go through neighborhoods, it's going to go through a house, through backyards, indiscriminately. It doesn't care. It's just going to go straight to where it needs to go. And that is what displacement is, as opposed to distance, which follows a very specific path. Okay? I hope this was helpful, guys. Oh, well, I actually have a blue jay there because in Texas, we don't really have too many crows around here. We have more blue jays and cardinals. So perhaps as the blue jay flies. That's not really a saying, but or you know what? As it occurs to me, maybe we should say as the hawk flies, right? Funny, yeah. All right, guys. Well, that does it. Here's again a summary of what we've been talking about with displacement and distance. I hope this video helped. Thanks for watching, guys, and good luck in your studying.